Apply the following terms to the graph of the AC voltage measured over time. First the definition and then the value. So how do you define what is period? We're looking for a definition first. So the definition should be what? The time for
it takes to say
when
the wave to complete 1 cycle.
Waveform begins and waveform begins through its rotation, comma, to where it begins to repeat itself. S-E-L-F-E-F, okay? To where it begins to repeat itself. That would be the best definition. The time where the waveform begins, and then through its rotation, comma, to where the waveform begins to repeat itself. And so in this particular illustration, if we look at this waveform, could we take the time from this peak, this positive peak, to this positive peak? Could we take that time? Yes, we could. Could we take the time from the negative peak to this negative peak? We could. The easiest place where most people will do this is if you're given a waveform that looks like this, and you have a starting point that is right at 0, the most people will start counting. Let's magnify this. Most people will start counting the number of squares between this point to this point. This is the waveform where it begins at 0 and goes in a positive direction up to a positive peak, comes down to 0, goes to a negative peak, and then back to 0. And it's at this point, this where my cursor is presently, where the waveform what? Repeats itself. So the definition that I gave, the time for when a waveform begins, through it, so here's the beginning point, through its rotation, and here's its rotation, to a point where it begins to repeat itself would be clearly, if I start at 0 time, would end right here. So your task is to determine what is that time. And so you can see that happens to align with 20 milliseconds, yes? So what everybody should have as a time answer would be 20 milliseconds. Enter. And so that's what you should have for the definition and the time, because you're asked for 2 things in this exercise. You're asked for definition and you're asked for value. Some people just gave me a value without the definition. Some people gave me the definition without the value. So you have to read the questions very carefully as you encounter them on the final examination, because if you only give me 1/2 of the answer, then you only get 1/2 of the credit. So you have to be mindful of reading instructions very carefully. Some people also gave me, and maybe they typed too fast. And let's double check this time frame and see if we're correct in our assessment of this. Waveform here, waveform ends here. And if I follow this line all the way down, does this division mark here in fact say 20 milliseconds? Everybody confirm that? So it says 20 milliseconds, and I saw some people type 2 milliseconds or 2.0. That would be an error. You may have read 20 milliseconds. You may have meant to type in 20 milliseconds, but because you were typing so fast or not paying attention, close enough attention to what you were typing, if you typed in a wrong answer, even though you saw and understood what the right answer should be, then your answer would be marked as what? It can only be marked as incorrect. So be very, very careful that as you observe what you think the time frame should be, that you actually type in and double check what you've typed in, because I've had some people type in 2 milliseconds instead of 20 milliseconds, and that would be a problem, okay? Now, based on 2 milliseconds, what is the definition for frequency? Frequency would be number of cycles per second. Very simply, that's all you have to say for the definition of frequency. And does this question ask for a definition. Yes, it does. What happens if you put down a frequency, some number without the definition? Then it's half wrong. Everybody pull out your calculator right now, because I'm going to be calling on names. The calculator should never be far away from you. For you to calculate what that frequency is. So what was the period of time? The period of time was 20 milliseconds. So you type in 20 milli, then you invert it, and you will have frequency. So what is your calculated amount of Hertz? So the definition of Hertz is the unit for frequency. That's your definition. And who's got a calculation for what that frequency is? Do you have that calculation, please? Let's see. Gabriel. Gabriel.
Yeah. I'm working on it.
Well, you type in 20 and you hit exponent negative what? Milli is what power of 10?
It's a -3.
Okay, so 20 exponent -3. Once you type that in, frequency and period are reciprocals of each other. So all you have to do is hit the reciprocal key.
50.
50, and it would be correct. So the number is 50, and it's capital H, lowercase z. So that would be calculated as 50 Hertz.
Okay.
Everybody understand that? Okay. So we'll go back here. So here is the definition part of the answer for period. And the period is given as 20 milliseconds. We determined that earlier. Frequency is the number of cycles per second. That's your definition. Now you can also state this. You can also state this up here. Period equals capital T, because that is the symbol for period. And so here on this line, you could say lowercase f is equal to 1 over capital T. It's equal to the reciprocal of the period. And that's how you would calculate the frequency at 50 Hertz, because it would be 1 over 20 milli. Okay. And then the Hz is defined as the unit of frequency. And this is, in this particular case, yeah, you could also type in 50, capital Hz here as well. That's fine. Right there. And I had some people type in a different number. Had some people type in something other than 50 Hertz, and it wouldn't be anything other than 50 Hertz, because your definition of cycle is going to be given this picture, 20 milliseconds, and 20 milliseconds, if you reciprocate it right here, can only be 50. So anything other than the unit of frequency, 50 Hertz, would be incorrect for the answer for this third line. Fourth line, we talked about this most recently. How would you define amplitude? Looking for a definition. Question goes to Pauline.
It's the maximum voltage. Wait, hold on. Maximum voltage of signal measured from ground, or 0 volts. That's what I have.
Okay. It would be from the 0 line up to the peak, yes?
Yes.
That would give you the positive V peak.
Correct.
Could amplitude also be not only positive V peak, but could it also be a negative V peak? Yes.
Yes.
Could it also be a peak to peak? Yes, it could. Could it also be an RMS value? Yes, it could. So amplitude is measured a number of different ways. The best definition for amplitude would be And we just did this
Signal strength?
signal strength. 2 words. Amplitude is nothing more than signal strength. And it happens to be given as V peak, V P dash P for peak to peak. It's also given as V RMS. It's also given as V average. So we did calculations for all of these, and all of these are different forms of amplitude, because amplitude can be measured as a V peak, peak to peak, VRMS, V average. And amplitude, oh, there's one more that we've talked about, dB, in decibels. Okay, so there's one more. Amplitude could be measured in units of decibels. If you're standing next to a column of speakers at a rock concert, yes, what's hurting your ears so much is the loud volume, and loud volume is measured in decibels. Okay, okay. So what would be the amplitude of this particular waveform? So the amplitude of this particular waveform, if we go to magnify this, and we would count from here, from the 0 line, 1 division, 2 division, 3, 4, 5 divisions. Wait, 1, 2, 3, 4. There's 5, but each one of these is worth 1, 2, 3, 4. Okay, so look at this very carefully. Look at this very carefully. You don't have, between 0 and 5, you only have 4 divisions in here, yes? So each one of these squares is worth how many volts? It's not 1 volt per square. Look at this very carefully, and I'll magnify this even more for you, okay? It's how are you reading? Basically what it comes down to is, how do you read a ruler? Okay, how do you read a scale? Let me magnify this right here. So magnify, 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 magnify. All right, so as you're looking at this picture, between the 0 line and the 5 volt line, how many squares do I have in between? 1, 2, 3, 4. I don't have 5 squares, I have 4 squares. So the natural inclination is to look at this very quickly and say, oh, each square must be worth a volt, so therefore this must be a 6 volt peak. This is not a 6 volt peak. How do I determine what goes on in here? Well, I've got 4 squares totaling 5 volts. So how much is each square worth? What do? What you do is you're going to take 5 and divide by 5 and divide by 4 squares. You have 5 volts, you're going to divide it into 4 parts. So how much is each square worth? Question goes to Kyle. I have 5 volts divided into 4 separate squares. How much is each square worth? You take 5, divide by 4, and what do you get on your calculator? Kyle.
1.25.
1.25 is correct. Each square is worth 1.25, 1¼ volts. So this is 1¼ this is 1¼ this one's 1¼ this one's 1¼ and you have one more 1¼ before you hit the peak. So what you do is you take 5 times 1.25. So 5 times 1¼ And so what value do you calculate this to be? Question goes to Christian.
6.25 volts.
Okay. Does everybody see that the value works out to be 6.25 V peak? And you have to put a little p there. Okay. Any questions on that? You'll see questions similar to this on your final, so you have to be very, very mindful how you read those squares. Okay, okay. All right. I think we've exhausted all the answers that are needed for question 4.1. Okay, okay. Now let us take a look at question 4.2. So as you take a look at question 4.2, let me go ahead and do a file save here. So file save as session 1, answers. And let me go ahead and save this in the appropriate folder here. Answers. Oh, all right. Looking at question 4.2, if the only instrument you had in your possession to detect AC voltage signals was an audio speaker, how would you use it to determine which of the two AC waveforms has the greatest period? How would you determine which of the two AC voltage waveforms has the greatest period? So that has to do with your definition of period right here. So let's come down here in this. So we would have to remember period equal the time for one cycle. Period. And period equals T. T equals 1 over F. And as period is equal to 1 over F, you're looking for the greatest period, but all you can do is with an audio speaker. Audio speaker is going to emit sound, yes? What do we expect to hear from here if we want an audio speaker to determine the greatest period? So right here, you would write greatest period equals, and look at this carefully. What is the relationship between period and frequency? Look at what's highlighted. I'm asking everybody this question. What is the relationship between period and frequency? I give you that formula. So given this formula, T is equal to the inverse of frequency. And that's the key, the inverse of frequency. What happens when period is bigger? Because we're looking for greatest period, yes? Right here is the key. So what happens when the T is big to F? If I make T go high for the greatest period, what happens to F? Does F go high or does F go low? And why? Question goes to Rolando.
So the frequency will have to be low.
Okay. So if the period goes high, that means your frequency goes low. LOW. Okay. So what would happen in this particular case is this. All that you need to do is, how would you determine which one? Because both of these are function generators. Both of these are generating waveform. Both of these have an output. I can hook up the speaker to the upper function generator. I can hook up the speaker to the lower function generator. How do I know which one of these will give me the greater period? Is when the frequency goes low. Right there. So when I hook up to the upper one, when I hook up to the lower one, what am I listening for? We should be listening for whichever function generator produces the lowest frequency we can hear through the speaker. Is everybody following what's going on with this? That would be how you would respond to this question. They're asking you to think which one of these two function generators, they're both producing AC waveforms, will give us the greatest period. And period we defined was the time for one cycle. And the period is given as the symbol T. And T has a very unique relationship to frequency. Frequency and period are the reciprocal of each other. In fact, I can add one more right here. Add one more. Let's go ahead and do this. F is equal to 1 over T. Okay, so there's your forwards and backwards of that particular formula. T is equal to the reciprocal of frequency. Frequency is equal to the reciprocal of period. So if I want greatest period, that means my frequency has to go greatest period, the biggest number here, means my frequency has to go greatest period, greatest period, greatest period. My frequency has to go low. So that as the T goes up, the F goes down. Or as the F goes, that's it. As T goes up, F goes down. And we can summarize that right here. As T goes up, my mouse is jumping. As T goes up for greatest frequency, comma, F must behave inversely proportional to T, and therefore must go down. There. Okay. That's your rationale. Any questions on how best to answer that particular question? You're using the speaker in your ears fundamentally, and what you understand about the relationship between period and frequency. Okay, cool. Take the next question. The next question says, a technician prepares to use an oscilloscope to display an AC voltage signal. Boom. After turning the oscilloscope on and connecting the Y input probe to the signal source test points, the display appears this way. What display controls need to be adjusted on the oscilloscope in order to show fewer cycles on the screen with greatest height? Okay, so there's two parts to this question, because here's the question here. So here's one question. Oop. And here's the other question. So this question is asking for two separate answers. And you happen to have some things here on the oscilloscope that you can play with. So which one of these will show fewer waveforms on the screen? And the best example of that particular guy was probably, let's see if I do this way. If I go to here, multi-sim and phase shift. Let's do the phase shift one is a good one. Yeah, I shouldn't have closed it. I should have left it in the background, but that's okay. Okay, can everybody see the, close this guy out. Can everybody see the phase shift circuit that we worked on earlier in this session on the screen? So we will go ahead, double click this guy. We see waveform. Well, we don't see waveform yet because we haven't activated the multisim. Reverse. Hit play. Okay, now hit reverse. And then hit stop. Move my cursor over. Okay. You have a tool by which you can test your answers for this particular question. This oscope is this oscope here. You have the means by which you can test your answers to this question. So there's two questions, keep in mind. How do we show fewer cycles of this signal on the screen? So right now, how many cycles do I have? It looks like at 1 and possibly 2. How can I show fewer cycles? What adjustment do I have available to me? We'll look at this very carefully. There's a big red knob that says vertical. There's a trigger control, and there's another big red knob that says time base. What do you think we should be doing? Question goes to Andrew. The hint is these three big knobs in red. What do you think we should do? What should we adjust in order to show fewer cycles?
I know in class you had us put them all down to 0 first.
Yeah, but we're given a waveform. So as we have a waveform on the screen, on this particular screen, we see many, 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 many cycles. And it's hard for us to read this many, many, many cycles. So we want to spread these out, such as what's shown here. This is nicely spread out. How do we get from here, where they're all packed together, so that they are nicely spread out? I have three controls that I can play with: vertical, time base, and trigger. Do you remember?
Time base.
Okay. And do you remember what time base does? What time has to do with, remember, your oscope is a voltmeter. It's a voltmeter that shows you voltage over a period of time. That's how it's different from a digital multimeter. You have a really nice, really boss digital multimeter in your hands you invested in, but that shows you an instantaneous value. An oscope shows you a continuously varying. So you get a nice graph here. So keep in mind, we have two axes, right, class? We have a vertical axis that measures amplitude, and we have a horizontal axis that measures time, and that time is measured in units of seconds, okay? So if we want to spread this wave out over time to go from many, many cycles in this particular guy to fewer cycles, then yes, you're absolutely right. We have to play with the time base. Come back here. Wait, never mind, go away. Okay. To show fewer cycles, we adjust the time base knob. And let's see if that's true. So on the oscope in multisim, your time base is right here. What is the time base set to right now? It's set to 50 microseconds, yes? And I can move this up, I can move this down. So if I go to do this, bring the time base down, I widen this. If I bring this, now I have many waveforms on the screen. If I do this one more time, oh, Don't I have something here on my screen right now that is similar to what I have in this exercise? Do I see many, many, many peaks out here? That's hard to read. And here I see many, 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 many peaks. So I play with my time-based control, take it from 500 microseconds per division, and then decrease this to 200, decrease this to 100, decrease this again to 50. Is this how I show fewer waveforms on my display? And yes, you're absolutely correct. We would use the time base because that changes the number of waveforms we have on the display over a period of time. Is everybody clear on why this answer needs to be time-based knob to show fewer cycles? And then how do I show greater height? How do I show greater height? In other words, amplitude. What do I adjust on my O-scope? So you have vertical, you have trigger, and you have time-based. Which one of these do I adjust in order to show a greater height? So the question goes to Gabe. What do you think?
You would adjust higher?
Well, there's nothing that says higher on here. So you have vertical, you have time-based, and you have trigger. So which one of these are we going to do? You want to show something that's higher. So what control do you do in order to make this higher?
I would say the vertical.
Mm-hmm. Do we have vertical controls for channel A and channel B on our O-scope? Our vertical on here presently is 5 volts per division, yes?
Yes.
So what was shown previously, was something like this, many, many waveforms. And what was shown previously was these guys here and here, okay? So we have many, many waveforms on the display. Does this picture presently look like the picture of our exercise? Many waveforms and occupying very little space on our screen. There and there, yes? So we already said, we already know how to show fewer. We show fewer by simply adjusting our time base. So now we show fewer. And you're right, Gabriel, that if we wanted to increase the height of the display, we have to go to our vertical control. So right here, to increase display of height, we adjust the vertical control. Okay, and let's go ahead and highlight that in yellow, and let's demonstrate this. So my vertical control has these really low, so I'm going to make this more sensitive by bringing this down. Bring it down from 20 to 10. Bring this down from 20 to 10. Bring this down from 10 to 5. Bring this down from 10 to 5. And in doing so, by adjusting the vertical controls, my voltage per division, keep in mind, vertical starts with what letter? V. Voltage starts with what letter? V. That's a good way to remember vertical control for height, is by adjusting the thing that says voltage. Therefore, we're able to increase the visual height of this exercise, which makes it easier for us to read. Any questions on that? Okay, cool. All right. So now let's go ahead and take a look at this next one. Control save. Okay, so now we're going to answer this question. So the question says, technician prepares to use an oscilloscope to display an AC voltage signal. After turning the oscilloscope on and connecting the Y input probe to the signal source test points, the display appears, boom, like this. Let's see if I can mimic that. And I'm going to take away one waveform. So do we have something? Yeah, pretty close. So does question number 4 Does this oscope display look like question number 4? I got a bunch of cycles and I can't see the peaks. Do I have a bunch of cycles and I can't see the peaks? So after turning on the oscope, this is what we have. So the question is, what display control, and see in parentheses, there's an S because there may be more than one, do you need to do as a technician in order to show a normal looking waveform on the screen? So the question goes to Pauline. What do you think we're going to need to do to make this more normal looking?
We
Pauline.
need to, hello, can you hear me? We need to, on the scale, we need to like lower it down. So from, sorry, my husband's on a phone call. Yeah, there you go. You need to lower it down so that we can see the peaks. The height is smaller.
So presently we're at 2 volts per division.
Right.
And so we can't see the top of this because it's 2, 4, 6, and it's past 6 volts. So we're probably going to need to adjust this from 2 volts to a different scale, yes?
Yeah, you need to lower it
Do I go-
down.
do I lower it to 1 volt?
I'm sorry, no, wait, higher.
Okay, yeah, we want to make this scale higher in order
Yes.
for the peak to come lower, like this.
Correct.
And if I go too far, it's really tiny. If I go really far, it's really tiny. So I don't want it to be too small. I want it to be as large as I can fit on the display without going over. So this is one step over. If I click here one time, it now fits the display. Yes, so now do I have a more normal looking display on the waveform, of a display on the scope? Closer in terms of amplitude, do I still have too many cycles on the display?
Yes. So
Yeah.
on
We don't
On
want
that-
this many.
yes. So you are going to lower down on the scale.
Which scale? I got 3
The
scales
seconds
here.
per division.
Okay, time-based scale. And what am I going
Time-based
to do
scale.
here?
Lower it down.
Okay.
Yep. So more. There you go. That
Yeah,
looks
because if
about
I
right.
go too low, I don't even have one cycle.
One cycle,
I need to get
correct.
at least one, if not more than one. So here I've got at least one and a little bit over. If I adjust this one more time, too many cycles. So the objective here when you're adjusting your oscope is to get as much of one complete cycle, but not over, and get as big a waveform as you can get, but not peaking over. So we don't want this situation where it peaks over. So it's got to be, in this case, 5 volt per division. And we don't want, this is too short of a time base because we don't even see one. This is too many, so we want it here. So we're going to adjust 2 things in order to make this fit, yes? So the most appropriate response to this will be vertical and time base controls. Okay. In order for us to achieve something like this. Is everybody all right with those answers? We have to adjust both.
Yes.
Okay. Now, next question. A technician uses an oscope to display AC, blah, blah, blah. After turning on it, it displays like this. What appears on the oscope is a vertical that moves from left to right. What display controls need to be adjusted in order to show a more normal looking waveform on the display? Let's see if I can mimic this at all. Let's put this in the run mode. This is about as close as I can get to the display of what they have here. It looks like a narrow vertical bar, and it's not showing anything close to what we've got. So what do I need to adjust in order for this to appear more normal looking? Question goes to Christian.
Lower the time base.
We need to adjust time base. Okay. And right now, this is at 1 second per division. So I need to adjust this to half a second, a fifth of a second, 10th of a second. Smaller, 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 smaller. Now I have something more normal, yes? So you're right. We not only adjust the time base, we need to adjust the time base to a lower time per division setting, period. Is everybody okay with this? So as I'm going through these questions and we're playing with these various aspects of the oscope, do you have a tool called Multisim on your computers that you can use to make these adjustments like what we're doing? And then you're going to get a recording of this a video of this so you can verify and understand your answers for this particular homework set of questions. The answer is yes, you do. Now you just have to make effort to do it. All right, and it says here for question number 6, a technician prepares oscope, blah, 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 and gets, boom, this display. What display controls need to be adjusted on the oscope in order to show a normal looking waveform? Question goes to Kyle. What do you think we need to do?
We need to zoom that out. It looked like it zoomed in on one particular spot on the waveform.
Correct. And how, which are we going to do? Which adjustment are we going to make?
Would that be time as well? And you just make it bigger?
Time base is correct. Spell this correctly. Time base. 2. So in the previous example, we had a lower time per division. So let me demonstrate that. So this waveform presently is not dissimilar to the waveform that's here, yes?
Yes.
Let me see if I can go one more. Yeah, that's closer. Okay. We don't even see all the way to the positive peak. And it's hard to even see the positive peak. So how do we get a more normal looking waveform? You adjust the time base, which is correct. And what do you said you want more time per division, yes?
Yeah, the opposite of the other one.
Right, so 5 microseconds, we're going to increase this to 10 microseconds. That's more time, that's double the amount of time, but that's not quite normal yet. We go from 10 microseconds to increase it to 20 microseconds. We're getting closer. Increase this to 50 microseconds. Hey, guess what? By increasing the time base, you show more waveforms. Yes? So time base was correct, and you want to adjust this to a higher time per division setting. Does that make sense to everybody? Because you need to practice this on your multi-sims to understand these questions. Okay, now this is interesting. Number 7, determine the frequency of this waveform displayed on an oscope with a vertical sensitivity at 2 volts per division and a time base, blah, blah, blah. All right, so how are we going to determine frequency based on this? So let's go ahead and magnify this puppy. Okay, that's about all we need. So we need frequency. That's all we want, just frequency. And a time base of 0.5 milliseconds per division. All right. Question goes to Gabriel. You want to try this? How do I determine frequency by looking at this guy? Frequency is measured horizontally or vertically? Gabriel.
I would say it'd be
Frequency is
horizontally.
measured- Yeah, frequency is measured horizontally. The only thing we measure vertically is amplitude, so that part is correct. So if we're measuring this horizontally, we are interested in the zero line and how the waveform goes from one point to another on here. So how do we use an oscilloscope display to determine the frequency? What do we do to do this with? What do you think, Gabriel?
You would have to, let me see.
So from earlier, just to give you a hint, from earlier, we discovered that frequency is the reciprocal of t. T was period, and frequency is the reciprocal of period. You're looking for frequency right here. Do I have period that I can throw into the calculation in order to throw in the formula in order to calculate frequency? Do I have some indication of time? Do I have some indication of time for one cycle in order to plug into that formula? How would I do that, Gabriel? Remember, time was horizontal. So how do I find the time for one cycle is the question.
Well, you would have to do some math, that's for sure.
Yeah, well, we need a number before we do the math. How do I find a number to work with? How do I find the time for one cycle is my question.
You count the squares on the graph?
Perfect. And you count them vertically or horizontally?
Well, horizontally.
Horizontally, good. Where would you start your count?
I would start, maybe in the bottom of the, almost like right when the graph is about to rise to the top of the rising point.
Okay, so here's, let's say we start here on this vertical line.
Right there.
So
And
let's say we start at this positive peak, because this is the same point, whether it's the bottom or the top. So let's say we start at the positive peak, the highest peak up here, this positive peak. Say we start there. Where do we end our count of squares? If we're starting here, where do we end our count?
in the bottom, there'll be 4 squares. Or no, it'll be.
Remember, the definition of a cycle is where the waveform begins, going through its rotation,
And
to where
where
it begins to repeat itself. So if we're starting here, where does the waveform begin to repeat
to
itself?
the next side up to the next corner of that, to the right.
The next positive peak. So if we're starting at this positive peak, the waveform starts to repeat at this positive peak. Are we in agreement with that so far? If I follow what you're saying, I think that's what you're saying.
Yeah, that's what I was.
So let's go ahead and count the number of divisions from this peak to this peak. This peak is just a little bit to the left of this line, yes? Isn't this peak to the left of this line? So can we count the number of squares between this line and this line?
5.
Okay, so we count, if we start here, this is 1, 2, 3, 4, 5 squares. Is everybody in agreement with me that we have 5 squares between the 2 peaks? Yes or no? Kyle, Andrew, Lau, Bolito?
Yes.
You have 5 squares. So you have 5 squares. Each square horizontally is worth how much time? 0.5 milliseconds per division. So what do you do? What you need to do is from positive peak to next positive peak equals 5 divisions, period. Then what you're going to do is 5 divs times 0.5 milliseconds per div calculates to be how much time? Everybody do the math. Pull out your calculators. I am looking for a number.
400 hertz.
There's 5 divisions and each one is worth half a milliseconds per division. So what do you have? 5 times a half. What's 5 times half a dollar? What's 5 times half a dollar? Come on.
400 hertz.
I'm looking for time first. Give me the milliseconds first.
2.5 milliseconds.
2.5 milliseconds. Okay. 5 divisions times half a millisecond division is 2.5 milliseconds. Then what you do, so that 2.5 milliseconds is equal to period, which is equal to t. Okay. What you want is f. What is the formula for f? F is equal to 1 over t, which is equal to 1 over 2.5 milliseconds, which then calculates to be, and the question goes to Pauline.
I got 400 hertz.
400 hertz would be correct. That is your process. Well done. Any questions on that exercise? So from positive peak to positive peak, we counted 5 divisions. Each division was worth half a millisecond. So 5 times a half gives you 2.5 milliseconds. What you just calculated is something called period. Period is the time for one cycle. Time for one cycle. And what you do, we needed to calculate frequency. Frequency is the reciprocal of period, or 1 over 2.5 milliseconds, which calculates to be 400 hertz. This step by step is what you do to answer those questions. That would be step 1. This would be step 2. This would be step 3. Okay. Now let me go ahead and put this guy out to here. All right. Any questions on that? Okay, let's take a look at the next one. The next question asks you, how is it possible to assign a fixed value of voltage such as 120 volts to an AC electrical quantity that is constantly changing, crossing 0 volts and reversing polarity? How is it possible to assign a fixed value of voltage or current such as this to an AC quantity that's constantly changing? So what it comes down to is this. The AC that you have in the walls, in our walls, the AC is constantly changing in amplitude. Spell this correctly. Changing in amplitude. Reversing in polarity. So as it's constantly changing in amplitude, like this waveform, our AC is a sine wave of this. Our AC is like this waveform here. That's what you have in the walls. It's changing from a positive half cycle to a negative half cycle, back to a positive half cycle, back to a negative half cycle. And it does this 60 times per second. So our frequency of voltage in our walls is 60 Hertz, meaning 60 cycles per second. And it's constantly changing, going from 0 up to some positive peak, back to 0, down to some negative peak. So PG&E gives us a number. PG&E tells you how much voltage you have. If you look at your appliances, you look on the back of your computer, look on the back of your toaster oven, you look on the back of your TV set, there's a plate, nameplate, that shows what type of voltage you are expected to plug that into. What is that voltage? It's got to be some number. So how do we assign some kind of a fixed value when this thing is constantly changing?
Find the RMS.
Yes. We will use the RMS value of AC to have a constant value of voltage, and per our friends PG and E, that constant value of voltage equals, so what's that constant value of voltage that PG&E swears is correct on our utility bills we get each and every month? What is that value of voltage?
120 volts.
120. You have to speak it out completely. It's 120 V RMS. Okay, that's what PG&E tells us, and that's how we assign one value. Because in reality, according to the waveform, it goes from 0 up to 169.71 volts peak. Back to 0, down to a negative 169.71 volts peak, back to 0. And it constantly changes. So we're not going to, we know that it changes, but we will use and abide by one fixed number, and that's the RMS value. That's why RMS is significant to us. Everybody okay with that answer to that question? Next, it says here, suppose a DC power source of 50 volts is connected to a 10 ohm load. How much power will this load dissipate? Well, if you remember, P is equal to IR. That's one formula. And P is also equal to V over R. And there's another formula also, if you look at your little cards. So do we have enough information here to do this? So PIV, PI squared R, and P V squared over R. All right, so we happen to have, this is actually, see if I can sneak this guy in here, make this a superscript. Home and script. Oops. Here. Superscript. Okay. All right. So you have this. You have this. Okay. Now, all right. So that being said, let's go ahead and take a look and see what we've got going with respect to this. 10 ohm load. So first, there's two questions. This question here. And then we want to connect it to a sinusoidal source with the peak voltage of this. We'll just do more or less. Okay, so two separate questions. So first thing you need to do is, first of all, calculate how much power will this thing dissipate based on this information. So you have a V and you have 10 ohms. So let's go ahead and do this calculation. What you're going to do is this formula here, and you're going to take 50 V, and you're going to square it, and then you're going to divide this by 10 ohms. And so this guy is going to be set up as a here. So how much power does this calculate to be? Question goes to Rolando.
It's 250 watts.
Okay, equals 250 watts. Anybody have any questions as to how that's calculated? Everybody good with that so far? Okay, okay. So next, since you happen to have the power that's dissipated equals power dissipated. The next part of the question has to do with this. The same 10 ohm load connected to a sinusoidal AC source with a peak voltage of 50 volts. Will the load dissipate the same amount of power, more power, or less power? So you don't just say, oh, same, more, less, and then walk away. What do you have to do? You have to explain your answer. So how do I go to approach this particular exercise? Pauline, you want to try this guy out? Or do you recall what it is you had submitted?
I did. I did the calculations where I did the same thing. The 50 volts DC applied to a 10 ohm load will dissipate 250 watts of power. So it's 50 volts peak sinusoidal. AC will deliver less than about 250 watts to the same load. That's a lot.
Okay, so let's see if you can go ahead and repeat that again. You're given a peak voltage of 50 volts. So what did you do with that?
So what I did was I also used the power formula.
Okay.
P equals volts squared divided by the 10 ohms. So it got me the
so
same
I'm going
thing.
to copy this guy and paste it here. So we'll start with this. And then what do you do with that?
So I did 50 volts squared divided by 10 volts. I mean 10 ohms. And it will give me a 250 watts of the same load.
Okay, so you're gonna, let's do copy. So you're gonna do this, yes? Is that what we're proposing? Volts squared. All right, how many people agree with this? Like a consensus of opinion or no consensus of opinion? Rolando, do you agree with this?
Yes.
Christian, do you agree with this?
I think it would be less wattage, no, because 50 watts is not the RMS value. That's just the peak value.
That would be correct, my friend. That would be enormously correct. So this approach you cannot use to calculate power in an AC circuit. We cannot use the peak voltage of AC. Power in an AC circuit, sinusoidal AC power, cannot be calculated using the peak voltage. We have to do this guy first. For AC voltage, we must convert 50 V peak to RMS. What was the relationship? What was the formula to calculate RMS from peak? You should have it readily available on your formula sheets in your notebooks. So V RMS is equal to what?
Volts
It is equal to 0.707 times peak. Or
Okay, so 0.707 and multiply by the V peak. 707, not 717, I'm sorry. Hit the wrong key here. 0.707, cool. Yeah, we use the square root of 0.5, but it's easier. Yeah, we can get pretty close with square root. I mean, with 0.707 is fine. So our VRMS is calculated by using 0.707 times the peak. Wow. Let's go ahead and pop that number in, 0.707, and we're going to multiply this by boom, 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 our V peak of 50 V peak. So go ahead now and make this calculation. And question goes to, Mr. Lau, give us this calculation if you would. We're going to multiply 0.707 times the 50 volt peak in order to get RMS. So 50 times 0.707 gives you what number, my friend? Mr. Lau.
I got 35.35.
35.35 VRMS would be correct. Okay. So what we need to do once you get the RMS value has to go here, not 50 volts, but it has to be 35.35 V RMS squared, and then divide by 10. And that will give you a different amount of power. And I'm looking for that amount of power. So 35.35, hit the square button, then divide by 10. Kyle, what kind of number do you have? 35.35, square it, and then divide by 10. What do you get?
1 second.
35.35 on your calculator, square it, and then divide by 10.
Divide by 10.
Yeah.
I keep getting an error.
35.35 divided by 10.
No, not 35, 35.35 square. And then hit equals. You might have to hit equals on your calculator.
Oh, okay, that's what's going on.
35.35 square equals, and then divide by 10. What do you got?
There we go. 124.96.
124.96 watts.
Watts.
Uh-huh. So, in conclusion, do we have more, same, or less?
something, somebody?
More power, less power, the same power.
In conclusion, it'd be less power.
Less power. It's a smaller number. Initially, we had 250 watts. Here, initially, we had 250 watts dissipated, and now we have 124 dissipated, so we have less power dissipated. Because why? The VRMS value is always less than the peak value. That's why. This would be your answer for this particular question. There's a couple of parts here, okay? So
Hey,
the first
Mr.
part,
I had a question.
yes.
So on the 35.35, you say you square it and you divide it by 10 and you guys got 124. I'm getting something else.
Well, did you didn't hear what I said to your friends a few minutes earlier, because they also had the same miscalculation. So what I said to our friends was this, listen carefully. You take 35.35, you hit square, and then you hit equals. Then divide by 10. Don't forget to hit equals after you square. Then divide by 10. Are we good?
Yeah.
What do you see on your calculator now?
Are you squaring it to the second or?
Yeah, x squared. Yeah, 35.35, and you hit the x squared key, then you hit equals. Then divide by 10.
Okay.
So what do you get?
124.96.
Perfect. Okay, so remember, because we're not all using the same calculator, you need to understand how to use your own calculator in order to get the result. On some of our calculators, we don't have to hit that equal button. On some other calculators, you need to hit the equal button. You need to know on your calculator, you do the first part of the calculation, 35.35, square, hit equals, then divide by 10. Okay? Okay. Good question. I'm glad we clarified that. All right, let's take a look at this next one. The next one says, determine V Rms amplitude of the sinusoidal waveform given this. All right, what are you going to do? Question goes to, let's take a look here. Belito, what are you going to do? Senor Belito.
Yeah,
What are you going to do?
we'll have to find the voltage peak first. All right, so it's gonna be 2.2. So we said 2.2 times 0.2 volts in order to find the B peak,
Okay.
first of all.
So the question here is this. Let me see if I can find draw, design, no, layout. I'm looking for here. Yes, got that. Got it in there. And then what I want is, okay. So what you need to do is you need to draw a line. Did everybody see me draw a line across the top of this? So as I drew a line across the top of this, the line lines up with the positive peak, because in order for us to determine amplitude, Rolando says we have to determine the V peak. So how do you determine the V peak of this picture, Rolando? Could you go ahead and repeat what it is that you asked now that I've drawn a line to the top?
I would multiply the numbers of division times 0.2 volts.
Perfect. So we're given a vertical sensitivity, 0.2 volts per division. So what you're going to do is here, you're going to multiply the number of divisions from the 0 V
Okay.
line up to the positive peak by 0.2 V per division. Okay, so how many divisions do you count from the 0 line up to the peak?
I guess looks like 2.1 then. Or 2.2.
2.1?
2.1 or 2.2?
Yeah, because if I move this line away, if this guy's right at where the peak is, like right there, and we go to magnify this, take this guy and I bring it right to the peak, which is right there. Okay. Now you're going to use a narrower pencil than I'm using in this drawing, but as you're counting this, each square is divided into 0.2, 0.4, 0.6, 0.8. Each square is divided into fifths, or each division mark is a 0.2. So it looks like our peak is sitting at 0.2. So you have two full divisions plus 0.2. So it looks like, I would go along with you, that we would have 2.2 divisions, and we're going to multiply this by 0.2 V per division will give us how many volts?
0.44.
0.44 volts peak, is that correct?
Yes.
How many people agree with
But
that?
when I hit the engineering, it showed me now different numbers, 440 milli.
Correct. Equals 440 milli V peak. That is correct. A decimal 0.44 volt peak is the same as, in engineering mode, 440 millivolt peak. That part is correct. So far you started this off just fine. Now the next part of the question is this. Next part of the question, our VRMS is equal to, and so we're going to share the wealth here. Let's see. Question goes to Pauline. Why don't you finish this up? How do I find my VRMS based on this?
We are going to multiply 400 p by the square root of 5, or 0.707.
Okay, so 0.707. We saw this formula earlier. So VRMS is equal to the V peak times 0.707. So in this case, we're going to take the 440 milli V peak, and we're going to multiply this by 0.707. And what do you calculate for our VRMS? Pauline.
I'm getting 311 millivolts peak. Oh, I'm sorry, 311.13 VRMS.
You're using the square root of 0.5?
Yes.
Excellent. Okay. those people who are not using square root of 0.5, you'll end up with 0.8 V RMS. And for the purpose of this particular solution, yes, we will have a more accurate answer if we use a square root of 0.5. It's just hard for me to type out in a word processor square root of 0.5. So we'll just go ahead and go with this. And that would be that. Any questions on this exercise and how this was done?
So the last
Question. Rolando, you had a question?
yeah, this the last problem in order to find which one should I consider for the vertical the BP value should I consider 0.444 VP or 440 millivolts peak?
Well, our answer, these two values right here are the same value. We've decided some time ago that we will always state our answer in proper engineering notation. So in proper engineering notation, the best form of the answer will be shown this way, 440 millivolt peak. But that is the same as the decimal value, a 0.44 volt peak. So if all we wanted was a V peak answer, then we better be answering 440 millivolt peak.
Yeah.
But
Okay.
0.44 is the same value. Okay.
Yeah, and for the final answer, I got my calculator said 311.08 millivolts.
RMS. If we use 0.707, and it would be 311.13 millivolts if we use the square root of 0.5. Okay.
So in the test, will you be requiring us to use the square root, or is point, I just want to be consistent.
I think I believe for the purpose of the final examination, if you just simply use 0.707, you'll get an answer that is closest to what the standard answer is expected. We've held ourselves to a higher standard in our class, but final examination is not of that same standard. It's a little less. So to answer your question, for the final examination, you can go ahead and use 0.707. Okay, good questions. All right. So this is a good review of this particular homework exercise. All right, I'll go ahead and save this guy. File, save, boom. All right, so that was one homework set.